Good day, everyone. Today we will be presenting our research on the sustainable high-yield extraction of cellulose from oil palm empty food sponge through subcritical water pretreatment. Here is the contents of our research. First, we introduce the background and relate study in the literature reviews. Then we highlight the research gap and define our objective and scope. Next, we explain the methodology and show our research timeline. Finally, we discuss the expected benefits and list the reference used in this study. The palm oil industry in Southeast Asia generates a large amount of Opefb, a biomass residue that is often discarded or used in low-value applications. However, Opefb is rich in lignocellulosic components, mainly cellulose, hemicellulose, and lignin, making it a promising raw material for value-added bioproducts. Cellulose, the major component of Opefb, is a biodegradable and renewable polymer with wide application in paper, textile, packaging, pharmaceutical, and advanced materials such as nanocomposites. Therefore, extracting high-purity cellulose from Opefb helps transform agricultural waste into useful products and supports the development of sustainable bio-based economy. Although conventional extraction methods effectively remove lignin, they also produce toxic byproducts and create environmental and safety risks. To overcome this issue, greener technologies such as subcritical water, ultrasound, steam explosion, and autoclave pretreatment has been explored. Among these methods, subcritical water is especially promising because it reduces chemical use while still breaking down hemicellulose and lignin. Therefore, this study focused on integrating subcritical water pretreatment with conventional process to lower chemical consumption, improve extraction efficiency, and support the sustainable utilization of palm oil biomass. Next, we will look at the related work by Susie et al., who studied the production of high-yield alpha cellulose from Opefb using thermochemical delignification. In that process, acidic bleaching with sodium chloride plays a central role in removing non-cellulosic components. From the FTAR result on the left, we can see that the main cellulose functional groups remains unchanged across different bleaching conditions. However, increasing the sodium chloride concentration and bleaching time effectively reduced hemicellulose and lignin. Under the optimized condition, 3.22% sodium chloride for 1 hour. The cellulose purity increased to about 83% with only small amounts of hemicellulose and lignin remaining. On the right, the XRD pattern clearly shows sharper cellulose peaks after acidic bleaching followed by alkali delignification. This indicates higher crystallinity with the crystallinity index reaching about 20%. The increase in crystallinity confirms that the treatment successfully removes amorphous components such as hemicellulose and lignin, resulting in a more ordered cellulose structure. Now, looking at the morphology of Opefb and cellulose fiber using SEM at 1000 times magnification, we can see the effect of bleaching. The treatment removed hemicellulose, lignin, wax, and inorganic material, leading to a more open and separate fibrous structure.
Next, we will discuss this study by Ahmad et al. Using oil palm mesocarp fiber with subcritical water and carbon dioxide pretreatment. This figure shows SEM images of OPMF before and after pretreatment at 500 magnification. The untreated OPMF had a rigid, intact surface, which limited enzyme accessibility. After subcritical water and carbon dioxide pretreatment, the fibers became rougher, and partially peeled, increasing the surface area and making cellulose more accessible for enzymatic hydrolysis. Building on the previous studies, demonstrate the importance of pretreatment in enhancing cellulose accessibility and product yield. From the study by Nochamsiana et al., a review on extraction processes of lignocellulosic chemical from oil palm biomass. This study reviews chemical, physical, and biological, highlighting their advantages and limitations to facilitate the selection of the most appropriate process. In our group, we chose a combined approach involving mechanical size reduction to increase surface area, followed by mild alkali treatment under subcritical conditions to obtain highly purified cellulose in an environmentally friendly manner. From these studies, the research gap becomes clear. Sushi et al. Used strong chemicals. Ahmad et al. Focused on mesocarp fiber, and Nochamsiana didn't test subcritical water on Opefb. So our work applies subcritical water directly to Opefb and follows with a middle bleaching step. Combine grainer pretreatment with efficient cellulose extraction. Next, I will talk about the aim and objectives of our study. Our aim is to extract high purity cellulose from oil palm M3 food bunch using subcritical water pretreatment combined with mild chemical bleaching. This method is expected to reduce chemical usage, improve cellulose quality, and be more environmentally friendly than conventional processes. Our objectives are simple. First, to cut down chemical use and make the process more environmentally friendly. Second, to produce high purity cellulose with improved physical properties. Third, to explore how this cellulose can be used in industries like paper and biocomposite. And overall, to support green chemistry and circular economy and add value to agricultural waste like EFB. Our research focused on cellulose extraction from Thai oil palm M3 food bunch. First, we investigate subcritical water pretreatment as a cleaner and chemical reducing method. We then compare it with conventional bleaching and lignin removal processes to evaluate efficiency and cellulose purity. This study is conducted exclusively at the laboratory scale, emphasizing chemical composition, structural analysis, and material characterization. Importantly, the work doesn't include pilot scale or industrial scale development.
Our experiment is divided into two parts: preparation of EFB symbol and alkali soaking to measure pH and observe crystallinity. After that step, the symbols are treated sub-water critical condition. Then we analyze the cellulose content after one full process called as one cycle, and our goal is complete to 20 cycles. For data collection, we focus on solid residue yield, chemical composition, and structural or morphological analysis. We use XRD, FTIR, NMR, and SEM to evaluate these properties. This is our expected research timeline. It may be adjusted depending on experimental conditions and results. Expected benefits include reducing chemical usage, obtain high purity cellulose, supporting applications like paper and biocomposites, promotes green chemistry, and adds adding value to EFB while reducing waste. Our reference come from 3 key resources, and here are the members of our group with Associate Professor Dr. As as advisor. We welcome any question you may have at this time. Thank you for your attendance.